That's so we already know how focal depth, near zone length, focal length are all affected by transducer diameter and frequency. They're directly related to the focal depth. All right. Sound beam divergence, just the opposite. Okay, just the opposite. Sound beam divergence. The diameter of the sound beam is the smallest at the end of the near zone. What's that also known as? End of the near zone. The focus, right? Also known as the focus, the focal point. That's also the beginning of the Fraunhofer zone, the beginning of the far zone, right? All right? Deeper than the focus, the beam diverges or spreads, okay? Beam divergence describes the gradual spread of the beam in the far field. Beam divergence describes the gradual spread of the beam in the far field. All right? Okay. So, just like focal depth, beam divergence also determined by transducer diameter and the frequency. Okay? Transducer frequency. All right? You have a question already?
Yeah. Is the focal or focus, it's a point or area?
It's a point. It's one spot where the beam is narrowest.
Okay.
That is this one spot right here where the
Yeah.
beam is narrowest.
Okay.
That one spot is just a point. All right. Okay. So transducer diameter and beam divergence. These two are inversely related, guys. Transducer diameter and beam divergence are inversely related. Basically, you can think of it as, because it has, just think about the focal depth as well. If the focal depth is shorter, then the beam is going to diverge sooner. It's going to cause more divergence. Okay. So it makes sense that these are inversely related and focal depth is directly related. Okay. Well, it makes sense to me. Smaller diameter crystals produce beams that spread out more or diverge more in the deep or Fraunhofer zone. Small diameter, see our crystal right here is a lot smaller than this crystal, a larger diameter crystal. Okay? That smaller diameter crystal is going to diverge or spread out more than a larger diameter crystal. Okay? Since larger diameter crystals diverge less, they improve lateral resolution in the far field. Of course, right? Because lateral resolution is determined by the width of the beam. Okay? Lateral resolution is determined by the width of the beam. Lauren, what determines axial resolution? Spatial pulse length. Yes, spatial pulse length determines axial resolution. The width of the beam determines lateral resolution. Okay? So, guys, that's transducer diameter, how it relates to beam divergence. Guys, again, I know how the book is, and it breaks down every single point. If you just remember the main points and know those relationships in the larger scale, then it's going to be all I need to know is that beam divergence is inverse related to the two characteristics that determine how much it's going to diverge, which are transducer frequency and transducer diameter. Okay? So remember, I know you guys don't try to just remember every single image or every single word, hang on to that. Understand those relationships, because that's going to help you answer the questions on the exam. Okay? So when it comes to frequency and beam divergence, also inversely related. Okay? Therefore, our lower frequency sound right here is going to diverge more in the far field than our higher frequency sound. Okay? Still, think about our focal depth, but we learned that's directly related, right? Mm-hmm. Our focal depth is still, more shallower in the lower frequency, showing that direct relationship. Our focal depth is still deeper, shown in the higher frequency, showing that direct relationship, right? That doesn't change. That's still the same. Okay? It just the inverse relationship is that the beam is going to spread out more divergence, lower frequency, smaller diameter transducer, smaller diameter PCT. Guys, I had a question the other day asking me, when we're talking about the transducer phase and PZT size, is that the synonymous terms? They are synonymous terms, okay? When I'm when I'm talking about transducer size or versus PZT diameter or transducer diameter, all of those mean the same thing.
Active element.
Active element, all of that. Crystal, ceramic, all of those terms are synonymous. Transducer diameter, same difference. Same difference, okay? I want to clear that up because I don't want any of you guys to be confused, because that is a little confusing because I am changing those words as I'm speaking. Okay? So again, frequency and beam divergence inversely related. Okay? Higher my frequency, the less divergence of my beam. Since higher frequency beams diverge less, they improve lateral resolution in the far field. Less divergence equals better lateral resolution. Okay? Less spread of the beam equals better lateral resolution. Okay? We like a thin beam because we need to be able to tell these structures that are not only parallel with the sound beam, but also perpendicular to the sound beam, meaning they're at 90 degrees from the sound beam. Okay? And that's how we get good lateral resolution. Okay? If the beam is so thick that it doesn't separate two structures, then those structures, again, they're going to be represented as one structure. Okay? And we need our beam to be as thin as possible so we can see the differences between these two structures. Just think about, say, for instance, in transverse imaging, where you can see the difference between the aorta and the IVC, even though they're side by side, right? But if we happen to have a wide beam, then those two structures are going to be represented as one structure. We wouldn't be able to see the difference in those two. Okay? So, axial resolution is parallel to the beam. Perpendicular resolution is two structures that are perpendicular to the beam or at 90 degrees to the beam. Okay? Axial resolution are structures that are parallel to the beam, are front to back, showing our depth. Axial resolution has to do with our depth, front to back. Okay?
Which is the x-axis, right?
Yes, you can say that. You
Yes.
can say that. Absolutely.
Okay.
Okay? Lateral resolution has to do with two structures that are perpendicular to the sound beam. So if my sound beam is traveling in a certain direction, I can erase this, not the flag, right? I know we have a clear for that. Right? Okay? So if I have, this is my sound beam traveling this way, guys. My sound beam traveling this way. Alright? So axial resolution would be structures that are parallel to the sound beam. Being able to, no matter how close they are, and think about our spatial pulse length. If our spatial pulse length is so big, it's not, these two structures are going to be represented as one. Okay? If our spatial resolution is able to go between those, then we're going to be able to identify both of those structures separately. Okay? Whereas this is axial resolution, this is lateral resolution. Lateral resolution deal with structures that are 90, our beam is traveling this way, right? So lateral resolution has to do with structures that are perpendicular to the direction that the beam travels. Okay? So
Yeah, so what happened because of this? What's the consequence of this situation?
being able to identify structures separately. So if our beam is too wide, then these two structures are going to look like this. They're going to look like one structure. Okay? But if our beam is thin enough to separate these structures, then we're going to be able to see both of those structures separate. Okay? That's the consequence. That's why we want a thin beam, so our thin beam can go in between the structures that are perpendicular to it and separate those as two different structures. We also want short pulses because our short duration events, so that these pulses are able to separate structures that are parallel to the sound beam, structures that are traveling in the same direction, such as, think about we're doing our liver is anterior to our kidney, right? So if we had a long spatial pulse length or long duration events, then it may not be able to see the difference between those the borders of the kidney and the liver. And I'm just using those structures like that would have to be a really wide, a really long duration event for it not to be able to see that. I'm just trying to give you guys that reference point because those are structures that are deeper, right? Sound beam traveling this way is traveling deeper, okay? These structures right here are perpendicular to the beam. They're at 90-degree angles to the beam, okay? So that's what we're talking about. We're talking about lateral resolution is perpendicular or 90 degrees to the beam. Axial resolution is structures that are parallel to the beam. Axial resolution is the most important. When we're talking about any kind of resolution, axial resolution is the most important of all resolution. We're going to learn about maybe like 6 or 7 different types of resolution. We've only started on these 2. Okay? But axial resolution when it comes to ultrasound imaging is the most important. Being able to see to image structures that are deeper in the body. Okay? But lateral resolution is also important as well, just not as important as axial. If you ever have a question of which resolution is more important, axial resolution would be the most important resolution. So then that's yes, ma'am.
So to get the actual, we would want, you said you want the lower?
To get what?
What did you say you wanted? Oh, you want more.
Better resolution is going to be provided with a higher frequency transducer. Okay? That's going to provide better resolution in the far field as the beam is diverging. The beam is converging in the near field. It's going to diverge and get bigger in the far field. Okay? Did I answer this?
No.
What's your question?
To get the more waves on axial, you said you wanted.
Short spatial pulsing, short duration events. Has nothing to do with this. Has nothing to do with this. So we were talking about short spatial pulsing and last chapter. This is more concerning. We're talking about beam divergence. It's more concerning lateral resolution. Okay? Beam divergence, that's changing the thickness of the beam. Remember I said lateral resolution changes along the length of the beam. As far as the beam travels, our lateral resolution at this point is different than it is at this point, different than it is at this point. Okay? Because the width of the beam is different in all those different points. Okay? So our best lateral resolution is always going to be at the focus, right? That's where the beam is narrowest. That's where the beam is the thinnest. Okay? That's where we're going to get the best lateral resolution at that point. Okay? We're going to be better able to identify structures that are perpendicular to the sound beam. Cool. All right. So, guys, when we're talking about least or less divergence, remember, inversely related to transducer diameter, inversely related to transducer frequency. Okay? So less divergence is going to be a large diameter transducer with a higher frequency transducer. Okay? So more divergence is going to be a smaller. And just look at our images. Look how much that beam is diverging or spreading out. Okay? There's going to be a smaller diameter transducer or a transducer with a lower frequency. Okay? So if we want the transducer, or we want to use the best lateral resolution, we want to have the one with less divergence. We want to have a larger diameter and a higher frequency. Is going to provide us with the best lateral resolution. Okay? A larger diameter transducer with a higher frequency is going to provide us with the best lateral resolution because there's less divergence, less spread of the beam in the far field. Okay? Our beam isn't going to spread as much. The more our beam spread, the worse the lateral resolution is. Okay? This lateral resolution is horrible right here because our beam, if we have 2 structures that are right here, I wish I could write on this wall, guys. We have 2 structures that are right here, then these 2 structures that are in this beam, if I have my aorta and IVC at this point, say if this is a transverse image, right? My aorta is always going to be on the left side, right? So aorta and IVC, if I had both of those structures within this one beam, they're not going to be separate. They're going to be represented as one thing, okay? But if I have my focus right here, aorta and IVC right here, then the beam is thin enough, it's going to be able to identify both of those structures. Okay? I wish I could write on that wall. I don't want to get in no trouble. I don't want to pay any. Okay.
The thin one is the lateral.
It's better lateral resolution.
Okay.
Better lateral resolution. Thin beam is going to
And
provide
which
some
is
better lateral.
better in axial?
We're not talking about axial resolution right now. When we're talking about axial resolution, we're talking about short spatial pulse lengths. Okay? So in that case, the higher frequency transducer is going to be better axial resolution, right? Because higher frequency is going to cause us to have shorter duration events.
Yeah.
Okay? But I don't want you guys to get that confused with beam divergence, because that's what this little section is about, beam divergence. Of course, higher frequencies are better than lower. We already know this, but we learned this 3-4 chapters ago. We like higher frequency transducers because they look better when we're talking about image detail. Right, Mama? When we went to lab that day, when we looked at the thyroid looked a lot better with a 12 transducer than it did with a 5 megahertz transducer, because we're not able to see the detail, the image detail within that thyroid with the 5 transducer versus the 12. If we had a cyst, I may miss that cyst on the thyroid with my 5 megahertz transducer compared to my 12 megahertz, because those short duration events are going to provide us with better image detail. All right. So when we're talking about divergence, again, these are the formulas right here, guys. Sophie loves these formulas. Clearly, the way I explained it, the pad is just like, PRP equals 1 over the PRF. I always say if it's underneath the fraction, that means they have an inverse relationship. That's my easy way to explain that. I don't want to get into why this is 1.85, why this is 1.2. It's no math. I'm not going to teach you guys nothing more.